SwayamPrabha. Digital India. Educated India.
Here we are going to start how we can use the small perturbation theory to the equation of motion of the aircraft and how we can come up with the linear model of the nonlinear system, because the aircraft equation of motion are highly complex and nonlinear. And to design the linear controls, we should have the system into linear form. Before we apply to the aircraft equation of motion, first let's study what is small perturbation theory and how we can use it to the aircraft system step by step. So let me write the heading: small perturbation theory. So here, why we have to consider for aircraft. So let me highlight the aircraft motion is governed by nonlinear differential equations due to the nonlinear nature of aerodynamic forces and moments, as well as the kinetic let me write kinematic and dynamic relationship involved in flight. The dynamic and kinematic equation we already found in the last lecture. These nonlinear equations, while accurate, are generally complex and difficult to solve analytically. Are complex and difficult to solve analytically. For understanding the aircraft behavior in response to control input or atmospheric disturbances. So basically the systems which are we derive for the aircraft equation of motion are highly complex and nonlinear. And to understand how the system behaves over time in linear regime, it is quite difficult. So we need to come up some linear form using the part-of-motion theory. Now, let's look what is a small part-of-motion theory. The essence of small part-of-motion theory is to approximate the nonlinear behavior of an aircraft around a steady equilibrium flight condition. The way we have done for the pendulum system in the beginning of the classical contour course part. So there, how you linearize the nonlinear equation of motion of the pendulum system using the small part equation in the equation of motion of the pendulum. The same way you will be proceeding here also. Flight condition. Generally we use often straight and level flight using linear equation. This is achieved by the introducing, this can be achieved by introducing small perturbation you can write small changes or deviation from the equilibrium point to the basically changes or deviation from the equilibrium point to the aircraft's state variables such as velocity, angle of attack, pitch angle, etc. And linearly relating these perturbations to the forces and moments acting on the aircraft. So this is basically how we'll be doing in the small perturbation theory to the nonlinear system. This here nonlinear system is the aircraft equation of motion. And let's look what are the different steps we have to consider for finding the linearized model of the equation of motion. Steps to linearize the equation of motion of the aircraft. this is the step we'll be following for finding the linear model of the nonlinear aircraft equation. The first step is we need to define the steady state flight condition. Define the steady state flight condition. Under this, first you have to identify a steady equilibrium flight condition around which the aircraft response to be analyzed. The same way what I have done for the pendulum system. So in pendulum system, we had two equilibrium point. One is upside down, another is above. So here we have one equilibrium point which is pi 0 and 0 0. So we generally we analyze the pendulum system about this equilibrium point, introducing the small perturbations. So for small deviation from the equilibrium point, how the system going to behave. So this thing we have done during the study of nonlinear equation motion of the pendulum system. We have discussed this part. So same way you can analyze here. This involves setting the time derivative of the state variable to 0, which implying no acceleration. This is the first part we have to do in the for finding the linearized model of the equation motion of the aircraft. And then we'll introduce about the equilibrium point will part of the system. So introduce perturbation. So here we shall introduce small perturbation. Introduce small perturbation with a state variable the same process will be following for the longitudinal motion and lateral motion. We'll be doing while we'll be deriving the linear model. These are the steps we'll be following. Perturbation to the state variables and aerodynamic forces and moment. If you, for example, if you consider the v is the steady state velocity of the aircraft, let's assume if v is the steady state velocity of the aircraft, a small perturbations, let's assume delta v is added It may be due to the external power disturbance or some noise in the system. It is not noise due to the external disturbance or the wind disturbance. So the V has been changed by the small part of delta V. So we can write is added, then we can write the total velocity is V plus delta V. So this is how we part of the state variable of the system. Then third step is linearize aerodynamic coefficient. The aerodynamic coefficient. So here we'll expand the aerodynamic coefficient. Basically, here expand the aerodynamic forces and moments using Taylor series around the reference point or the equilibrium point, around the equilibrium, and retain only the linear terms. So here we'll neglect the higher order terms, assuming the perturbation. If the perturbations are very small, we can ignore the higher order terms. So I can write higher order terms are neglected, assuming the perturbations are small. And the final step is not final step. So from this step, we'll find the linear equations for and derive the. So basically what you are doing, we'll retain only the linear terms in the part of equations. We'll neglect the coupling term or higher order terms. Then we'll come to derive the equation of motion in linear regime. Derive the equation. So here we'll substitute the part of variables and linearized aerodynamic expressions into the original non-linear equation of motion. This result, this step results, this result a set of linear differential equations that this equation will derive in first order ODE basically. So just the degree of the order of the equation will be one, first derivative only. Equations that describe the dynamics of the aircraft in terms of linear differential equation in terms of, we can write the part of this linear differential equation will be in terms of part of from the equilibrium state. So assume, suppose we had velocity of the aircraft was, for example, capital V, and due to perturbations, this velocity has been changed V plus delta V. The Fortov equation will be writing in terms of delta V. So our main motivation is we need to design the control such that delta V is going to zero. Then if delta V is going to zero, the V will be equal to this same V here. So this is the main motivation. So the linear model will be finding in terms of part of variables. Final step is simplify the equation of motion into state space form. So once we have the linear equation of motion of the aircraft system, we can write in state space form. Here we are going to work on two set of equation of motion, which is longitudinal motion, another is the lateral directional motion. So for both the equation of motion, we'll come up with the state space form, and we'll be designing the control system. And also how we will be looking how we can find the single input and single output equation from the state space model. Those part also we'll be looking at. Okay, the final step is simplify into state space form. So here the linearized equations are further simplified and arranged into a state space form. How we can come up with the state space form? There, those part already have explained. The pendulum system, we assume that is the second order system, and how we can come up with the two OD form, ordinary differential equation form. So, and also we wrote that system into state space form, and which makes the easier to analyze the system. So making it easier to analyze the system using control theory technique. Since in this course we are going to dealing with the linear control theory, so the system needs to be written into linear form. So that is the main motivation why we need to consider this perturbation theory. If you are designing nonlinear control, we can go as it is. we can take the equation as it is and we can move on. Nonlinear equation we can take as a reference dynamics. We can design the control. Since we are designing the classical control or modern control for this aircraft system, the system needs to be written into linear form. Let me write one more sentence here. The state space model consists of matrices that represent uh, the dynamics and control input effect on the aircraft are part of state. So if you remember, after linearizing the system, if you write in state space form, we can write x dot equal to ax plus bu and y equal to this u and y equal to cx plus du. So here is the control matrix and this is the output matrix. So this is how we can define the nonlinear equation, higher order equation into state space form. So these steps will be following for finding the linearized model of the equation of motion of the aircraft. We'll introduce the perturbation, then we'll write the Taylor series expansion, and from the Taylor series expansion, we'll ignore the higher order terms or coupling terms, and we can come up with the linear model. And also the linear model we can write in state space form as well. Now we'll take our system. The first system we are going to take the longitudinal motion and how we can apply this perturbation theory to come up with the linear model of the longitudinal equation of motion of the aircraft. Before that, we need to apply the perturbation to all variables and how we can write the part of variables of the reference states. So let me write all the variables in the equation of motion are replaced by our reference value plus a perturbation or disturbance. As I have written here, that if the v is the variable, for example, here v, and due to the perturbations or due to the disturbance, the variable is shifted by delta v, for example. So we can write v plus delta v. So this is the direction. So this is how we need to, due to the perturbation, we need to apply this perturbation to all the states in the equation of motion of the aircraft. So let's look how we can write the state variables into part plus reference part. So for let's see, u will be the variable which constitute the reference part u naught and delta u. So delta u due to the perturbations and u naught is the trim value or reference model of the aircraft. And then v equal to, we can write v naught plus delta v and double equal to, we can write double naught plus delta W. So, but we have the equation we have written in terms of U V W. Why? Because in our equation we have disturbance as well as the original product in the equation. So that's why we can write U V and W. And similarly, if you apply the perturbation to the rates, we can write P equal to P naught plus delta P. So P naught is the reference value and delta P is the perturbed part for the variable. And Q equal to, we can write Q naught plus delta Q, and R equal to R naught plus delta R. And similarly, if you apply the perturbation in the force terms, so you can write X equal to X naught plus delta X, Y equal to Y naught plus delta U, so Y, and Z equal to Z naught plus delta G. And similarly, in the moment, M equal to M naught plus delta N, and N equal to N naught plus delta N, and L equal to L naught plus delta L. And if you apply the perturbation to the angles, phi theta psi, so theta we can write theta naught, the reference value plus part of part delta theta, and phi equal to, we can write phi naught plus delta phi, and psi you can write psi naught plus delta psi. So these are the perturbations we apply to the state variable for the reference state of the aircraft. And since we have mentioned the reference model of the aircraft will be assuming level or level flight. So for the level or flight, let's look what should be the values, reference values should be. And before that, let me consider another assumption to the system. The reference flight condition is assumed to be symmetric and propulsive forces assumed to be remain constant. In this condition, we can write, this implies that, so in this condition, if you consider this is the reference flight condition, then we can write V naught equal to P naught equal to Q naught equal to R naught, and phi naught and psi naught equal to 0. So for the reference flight, for this condition, estimating the propulsive force assumed to be constant, in this condition, we can come up with this is the reference state to be maintained. And okay, this will be psi naught. Now we'll assume the longitudinal equation of motion, and for this reference values of the state, and let's look how the trim condition, what should be the trim condition for the longitudinal motion of the aircraft. Okay, so first let me rewrite the equation of motion for the longitudinal motion. The longitudinal motion equation of motion. So this is already we have written in the last lecture. So let me rewrite again. X minus mg sine theta equal to m into u dot plus qw minus rv. So we need, in longitudinal motion, we need to consider the force along x-axis and z-axis and the moment along y-axis. So you can write moment should be along x-axis as well. So I can write g plus mg cos theta cos phi equal to m into w dot plus pv minus q, and moment equation should be for the longitudinal motion m equal to, moment should be in the y direction so that we can control the pitch axis of the aircraft. Q dot I y plus PR ix minus iz plus p square minus r square into ixg. Now, for this reference model, let's look the what should be the trim flight condition for the longitudinal motion of the aircraft. Let's look. Hence, the reference model or trim flight longitudinal equations at the trim values P naught equal to 0, U naught equal to 0, R naught equal to 0, and V naught equal to 0, and phi naught equal to 0. So this condition actually, the rates of the aircraft at trim condition should be 0 actually, the rates. And this is basically side velocity, and this is level flight. So these are the conditions needs to be maintained for the trim condition of the longitudinal flight of the aircraft. Under this condition, the equation motion of the longitudinal equation aircraft, we can write, let me define this equation number 1. So under this condition, equation number 1, written as x naught minus mg sine theta naught equal to m u naught dot and g naught plus mg cos theta naught equal to m w naught dot and total moment along y-axis should be 0. So this is the equation number 2. The trim flight for aircraft equation of motion. And now let's look what should the trim flight condition of the lateral directional equation. So let us rewrite the equation motion of the lateral directional equations of the aircraft. The lateral directional equation of motion can be rewritten as so in lateral directional motion, we'll assume the force along y-axis and movement along x and z-axis plus mg cos theta sin phi equal to m into p dot plus ru minus pw, and moment along x-axis p dot ix r dot ixg plus qr ig minus iy minus ixg pq. And the moment along z-axis n equal to minus p dot ixg plus r dot ig plus pq iy minus ix plus ixg qr. So this is the lateral equation of motion of the aircraft, lateral directional motion of the aircraft, and the trim flight for the lateral direction equation we can write. So we can write steady state trim flight for lateral directional equations at p equal 0 equal to 0, q not equal to 0, r not equal to 0, and phi not equal to 0. At this condition, we can get the trim flight condition for lateral directional equation y naught equal to m v naught dot l not equal to 0 and n not equal to 0. So this is equation number 3. Trim flight condition for lateral directional motion of the aircraft. So these are the model we'll be requiring while finding the state space model, which we'll be writing in a part of variable form. Let's stop it here. We'll continue from the next lecture how we can find the linearized model of the longitudinal equation of motion of the aircraft. Thank you.